Hello students, welcome to the concept current gain of CA amplifier with resistive load RL. The topic is at high frequency. The last video I explained the current gain of CA amplifier with output short circuited, means the short circuit current gain of CA amplifier. And we derived F beta and Ft also, and I have drawn the frequency response and for that case. Here the concept is, if the output is connected with a load resistor RL like this, if the output is connected with load resistor RL, what will be the current gain of the circuit? Okay, so let us start the derivation. So before deriving, you have to simplify the circuit. The circuit is very big, you have to simplify the circuit. So for that, the first concept is compare RCE and RL. RCE is the output resistance which is very greater than RL. So RCE is far greater than RL. Therefore, the parallel combination of RCE and RL, see the parallel combination, RCE and RL is approximately equal to RL. Because high value of resistance in parallel with low value of resistance gives low value. So you can neglect this, means you can open this RCE, neglect means you can open this RCE, and at that time the circuit, at the output circuit only consists of the resistance RL. Okay, that is one point. Another point is, say this RB dash is C and CB dash is C. What is this side? This side is input side. Okay, and what about this side? This side is output side. If you observe these two, RB dash is C and CB dash is C, both are between input and output. Okay, means these two elements are connecting output and input. So that is the reason these two are called feedback components. Means the two components are shared by both input and output. That is the concept of feedback. You know it very well. Okay. So now as RB dash is C and CB dash is C are shared by input and output. But we have to find the current gain, which is output current by input current. So there is a need to separate this RB dash is C and CB dash is C to the input side and for the output side. Okay, to separate these type of components which are connecting the input and output, we have a theorem called Miller's theorem. According to Miller's theorem, the circuit is like this. Yes, this is a circuit after the application of Miller's theorem for the two components RB dash C and CB dash C. See, by applying Miller's theorem, you can separate these two components. Take first RB dash C. With the help of Miller's theorem, we divided RB dash C into two parts. One is the input side part, another one is the output side. The input side part is RB dash C by 1 minus K. And the output side part is RB dash C into K by K minus 1. What is K here? K is nothing but amplifier gain. I'll tell you. Then now we'll take the CB dash C. CB dash C also divided into two parts. One is XCC divided by 1 minus K, means its reactance is divided by 1 minus K. And here it is XCC into K by K minus 1. Okay. So in that way you can separate these two as components RB dash C and CB dash C with the help of Miller's theorem. Now I'll tell you what is this K. K is called amplifier gain. So what is K? V naught by Vi. What is the output voltage here? V out divided by input voltage is VB dash. This is input voltage and this is the output voltage. Current through the load resistor is IL. Okay. So now, what is this V out? We know V out means the output voltage is ILRL. Then if it is ILRL, what is IL here? IL is nothing but minus IC. Both are in opposite direction. And IC is equal to GM VB dash E. So it is minus GM VB dash E into RL. Okay. Only I am considering the current part. The current is approximately equal to GM VB dash E Okay, so that implies your K is minus Gm Vb dash E into RL by Vb dash E. So what is this? Minus Gm RL. So as an example, to simplify the circuit furtherly, as an example, let Gm as 50 milliampere per volt and RL as 2 kilo ohm. So I will get K as minus 50 into 10 power minus 3 into 2 into 10 cube. So it's nothing but minus 100. Okay. This RB dash C by 1 minus K. Yes, RB dash C by K is minus 100. So it is 101. RB dash C is the typical value of RB dash C is 4 mega ohm to 5 mega ohm. So consider 4 mega ohm. 4 mega ohm by 101 is approximately equal to 40 kilo ohm, which is very greater than RB dash E. So in the input circuit, RB dash E and RB dash C by 1 minus K both are in parallel. RB dash C by 1 minus K is far greater than RB dash E. So the parallel combination of these two gives only RB dash E. So you can open this RB dash C by 1 minus K. Okay, another point. Here, I'll consider this now. RB dash C into K by K minus 1, that is minus 100 by minus 101. Approximately these two are same. It is RB dash C, approximately RB dash C, which is far greater than RL. So in the output side, only RL remains. The parallel combination of RL and RB dash C by K, RB dash C into K by K minus 1 gives only RL. So yes, you can keep this RL and you can open this RL. Okay, and other part. XCC by 1 minus K. I'll explain XCC by 1 minus K. XCC by 1 minus K means 1 by J omega Cc by 1 minus K. That is 1 by J omega Cc of 1 minus K. Okay. Without the Miller's theorem, the capacitance is Cc. But with the Miller's theorem, the Cc gets multiplied by 1 minus K and it is at the input side. What is the other capacitor at the input side? See the other capacitor? The other capacitor is this Ce or Cb dash E. Okay. So that gets in series. So this Ce, the other capacitor is Cc into 1 minus K. So what is the total capacitance? The total capacitance becomes Ce plus Cc of 1 minus K. Okay, that is Ce plus Cc of 1 plus GMRL. Okay. Now coming to this output side capacitance, XCC into K by K minus 1, as this RB dash C into K by K minus 1 is approximately RB dash C. XCC into K by K minus 1 is also approximately equal to XCC. Means the capacitance here is only Cc, which is very less compared to this. Because it is, yes, here the component is 1 plus GMRL, which is very high. Okay. So this capacitance is very less compared to the Ce plus Cc of 1 plus GMRL. Okay. So totally you can neglect the capacitance in the output side. Okay, fine. Now I am drawing the total resultant circuit. RBB dash. Yes, RB dash E is there. Voltage across this is VB dash E. And this is the terminal B and this is B dash. And you have a capacitor called Cm, I can say, where the Miller capacitance Cm is CE plus CC of 1 plus GMRL. Okay. The reason for the Miller capacitance is we obtained that because of the Miller's theorem. And at the output side we have the current source GMVB dash E and only the resistance RL. And here is the current IL, collector, IC, emitter, this is emitter, that is grounded. And what is this? This is nothing but your output voltage. Okay. So this is a simplified circuit. Now we'll move to the current gain AI, IL by II. What is IL? Minus IC. IC is GMVB dash E minus GMVB dash E by. So the input side, let it be IN or II. So what is II? I'll go for voltage into conductance. I explained it in the last concept, CE short circuit current gain. VB dash E into, you have to go for the conductance of these two branches. The first branch conductance is GB dash E and the second branch conductance is J omega of Cm, I can say Cm. Okay, so VB dash E cancel. Minus Gm by GB dash E plus J omega of CE plus CC of 1 plus GMRL. Okay. Then AI. What is GM? HFE into GB dash E. GB dash E plus J omega of CE plus CC of 1 plus GMRL. Okay. So now cancel your GB dash E. You'll get minus HFE by 1 plus J omega of CE plus CC of 1 plus GMRL divided by GB dash E. I'll write omega as 2 pi f. So 1 plus J 2 pi f of CE plus CC of 1 plus GMRL divided by GB dash E. Implies the current gain AI is minus HFE by 1 plus J F by FH, where FH is GB dash E by 2 pi of CE plus CC of 1 plus GMRL. Okay. Therefore, mod AI is HFE by root 1 plus F by FH whole square. Then, what is FH? I can say it is the frequency at which current gain with resistive load decreases by 1 by root 2 or 3 dB from its low frequency value. That is, you know, at f is equal to 0, what is AI? HFE. That is the maximum value. But at f is equal to fh, your AI becomes HFE by root 1 plus fh by fh whole square. So that is HFE by root 2. So it gets decreased by 1 by root 2, or if you convert it into dBs, the dB gets decreased by 3 dB. Okay. Another important point is, what is actually fh? Fh is GB dash E by two pi of CE plus CC of 1 plus GMRL. Okay. It implies when RL is equal to 0, keep this RL is equal to 0, then when RL is equal to 0, FH becomes GB dash E by 2 pi of CE plus CC, which is nothing but F beta. So when RL is equal to 0, FH and F beta both are same. Okay. As RL increases, so if you see RL increases, it implies FH decreases. These are the observations. So the maximum value of FH is F beta, because you'll get maximum value when RL is equal to 0. So the maximum value of FH is F beta. For all other RL values, FH is less compared to F beta. Okay, so these are the observations. Okay, so this is about the current gain of CE amplifier with resistive load. We derived the current gain as, this is the current gain, HFE by root 1 plus F by FH whole square, where FH is this, and these are the observations from the derived value. Okay, so I think you understand the total derivation. Okay, listen carefully and write the notes also. Very easy topic. Okay, thank you very much.
Thank you for watching this video. If you like this video, please don't forget to like, share and subscribe.